let's roll in here. So we're talking about a finitely generated. Again, we're talking about finitely generated modules over PID. Then A and this was the free part. So if you have a finitely generated module of PID, it breaks up into a direct sum of the free part, which is also a finite rank. So finitely generated free, and a torsion part. So every element of here is killed by some non-zero element of the ring R, and F is isomorphic to A mod AT. So we can get a little bit more specialized in how that breaks down. The last theorem that we had last time was this theorem 717. So the strategy for this is as follows. In a certain sense, F is easy, right? Because it's free and it's a finite rank. So really all you have to know is what is the rank of it, right? And so if the rank is n, including 0, it's that many copies of the ring R. The interesting part is the torsion part. So we got to kind of pick that apart a little bit and figure out what it looks like. But the torsion module over PIDR, and let P be a non-zero prime. And excuse me, and AP this is the set of stuff in A such that PKA equals 0 for some K. So this is the stuff in A that's killed by some prime. Then A is isomorphic. And if A is finitely generated, then D then AP, that is, equals 0 for all but finite rings. Okay. Questions on that? Yes, sir.
For saying P is prime, doesn't that mean it's already not equal to 0 by definition?
No, 0 is always a prime identical domain. So let me break this down further. Seven point 1.8. Every finitely generated torsion module M over PID M over a PID R can be written as a direct sum as can be written as a sum of M copies of these submodules, or I guess D copies of that, where each MI is cyclic. And we'll say that PINI annihilates MI. So that is to say that MI is isomorphic to R mod where NI is the minimal NI that annihilates, such that P out of the NI annihilates MI. And by the way, you've seen, this is the analog of what you've seen before. In fact, let me give you the next step, and then I'll kind of put it together with some examples. This is sort of a familiar theorem you're probably used to. So let me write this up. I'm gonna do this in terms of invariant factor decomposition and elementary divisor decomposition, and I'll show you an example that's Z modules. So it'll probably be familiar theorem. Theorem 719. Let A be a finitely generated module of PID. Logic. Number one, A is the direct sum of a free module of finite rank. And a finite number of cyclic torsion modules. And let me point out that the number of the rank of the free module could be 0. You might have no non-trivial free part, and the number of torsion modules might be 0. These cyclic torsion summons are isomorphic to R mod TIR, where each TI is a non-zero non-unit of R. And they can be arranged so that by T2 by. These are called, the TIs are the invariant factors. And this list of invariant factors and the rank of the free part completely determine what A is of isomorphism. Let me point out here, let's see, I say each TI and R is a non-zero non-unit. Why is that? Well, if TI is 0, then R mod 0 is R, right? Which is another piece of the free part, right? So we wouldn't bother with that, would we? And if TI is a unit, it might as well be 1, and R mod R is 0. And so you've got a cyclic 0, and why would you bother with that? This is called the invariant factor decomposition. On the other hand, you can do this another way. So this is an alternative. So I can start this off the same way with a free part or finite rank. The torsion part of A we can now sort of list this in a different decompose this a different way, is a direct sum of cyclic torsion modules each of which is isomorphic to R mod PISI. So notice these TIs right here, I don't care whether they're prime, the big thing is they successfully divide each other. Here, I'm making what I'm modding out by be actually a prime power. Where each of these PIs is in fact prime. A list of primes P1, P2, K, and exponents. Let's say S1 up to SK, completely determined. Torsion part. All right. By the way, let me point out that these primes here in my list do not have to be distinct. You might double or triple or quadruple up on any number of these primes. These are called the elementary divisors. And the elementary divisors and the invariant factors actually determine, when we get to it, actually help determine different canonical forms of the matrix. Let me, how about, does this look familiar to you all? Let me do actually a concrete example here that may help, I hope. Example. Something concrete here. Find invariant factor. And elementary divisor. Decomposition. I'm just gonna give you a torsion group, right, because I don't care too much about the three part. Because that's always the same for me, anyway. Let's make something. Uh. hmm. Now, I don't know about you guys, but I've always wondered what the decompositions of this particular group are. So suppose I give you this group, I may end up regretting this. Let's see. The first thing I want to do is I'm going to break this up because I don't know if you remember this, but this holds over a PID too. But here's a key fact: if GCD of A and B is 1, then Z mod AB and vice versa, ZA correct something. Right. And this is actually true over any PID. And so what this allows me to do is I'm going to take each one of these pieces parts here. So let me write this up. And it's whole boring here. 20. 100. 100. Z98. Z36. I got them all, didn't I? Yeah. Okay, so what this first bit allows me to do is I'm going to clean this up a little bit. I want to write this in prime power decomposition, right? And 18, I guess, is 3 squared times 2, right? So let's do this. This first piece is Z9, correct, some Z2. There's my 18. Now, this is something, this is 2 to 5 times, oh, actually it's 4. So this is Z4. And now I've got what 105. So that's Z3, Z5, Z7. There's my second one. It's 420 in prime power. And this is just 420 times 5, isn't it? So this is Z4, Z3, Z25, Z7. Everybody okay? 56 is 7 times 8. So, oops, nobody's wanting to still going. Z7, Z8. 100 is Z4, Z25. 98 is Z2, Z49. 6 is Z4, so Z9, and finally Z32. So sorry for that. Everybody okay so far? Okay, so let me do elementary divisor first. Although you certainly don't have to, you can do it either way first. What I want to do elementary divisor is I'm gonna just go through and I'm going to pull out. I'm gonna go prime by prime, right? So. A is actually more big. Okay, let me look at the prime two. Let's see. I've got a 2, 4, 4, 8, 4, 2. I got a 2 in every one of these. And I'm gonna go biggest to smallest. Okay, I got a 32. And there was an 8 there somewhere. And I've got how many 4s? 1, 2, 3. I've got 4 copies of Z4. And see, I had 4 copies of Z4, and that leaves me I guess 2 copies of Z2, right? So, for example, in this elementary divisor list, my first 8 primes would all be 2, power 5, 3, 2, 2, 2, 2, 1, 1. So my elementary divisors corresponding to prime 2 are 32, 8, 4, 4, 4, 4, 2, 2. Now let's move on to 3. See what I've got there. I have a 9 and a 3 and a 3. No 3, no 3, no 3, and a 9. Looks like I got what, 2 9s and 2 3s, right? Okay, corresponding to the prime 3, there's that piece. All right. 9, 9, 3. Okay, I guess I've only got 2 more primes, right? I've got 5 and 7. So for 5, let's do 5. What do I have? I've got 5, 25, 25, and that's it. So I got 2 25s and 5. And finally, 7. What do I have for 7? Not much left over. I got 2 7s and a 49. So we're going to send it again. Sorry? Is there a 37? Okay, 1, 2, wow, there sure is. 3. Yeah, so I need to check on another one here. But 7,200. Okay, so this is the elementary divisor, right? Everything's in prime powers, right? It's the direct sum, this. And so it's all nice and in terms of prime powers, right? Okay. with it? How many of you have seen this before? Have you ever done this kind of computation? Do you know how to get the invariant factors from this? I'm gonna sort of do this in reverse order when I do this. Once you have the elementary divisors, I always think it's easy to do this. You can do it in the other order as well. To do this, to do the invariant factors, I'm going to use this in reverse. Right? The biggest cyclic piece that I can make of this by the way, before I do this, can anybody tell me how many cyclic summands I'm going to have in my invariant factor decomposition? Good, good. So to make the biggest one, glue the biggest pieces together, right? So whatever this is, 2 to the 5th, 3 squared, 5 squared, 7 squared. And that's the biggest piece taken. That's your biggest chunk. The next one, yeah, it's kind of a greedy algorithm. You just go down here. See, 8, 9, 25, 7. So that's what 200. Oops. To 7. I think I did that right. Next piece. And third thing. And so let's see, that's well, it's 105 times 4. And now I'm out of the prime 5. All right, but I can keep going. 4 times 3 times 7. And now I'm out of every prime except for 2. Right. And so the rest of this is just the tail end of this. And there you go. Notice that now my invariant factors are, I did this in the other order, are in order from smallest, biggest 2, 2, 4, 4, 84, 20, 12,600, and this number right here. And notice that they each successfully divide, everyone divides the next. Okay. And this is basically the same thing that we're saying in this. This works over any PID because what did I do here? This is Z mod prime powers, and there's nothing different about a PID. It's R mod prime powers doing exactly all the same stuff. Okay, any questions on that? So this is modules over PID. It's essentially exactly the same thing that you got when you look at finitely generated abelian groups, right? You have 3 parts that's finitely generated. You've got this torsion part, and you can be fancy and decompose it, elementary divisors or invariant factors. And here is our big application for this. decomposition of a single linear transformation. And these are the so-called canonical. So in your travels in the past, what do you all know about canonical forms, if anything? Right? Maybe some of you are doing this, maybe you haven't done it yet in 8530, but how many of you have heard of the Jordan canonical form? Do you know anything about the Jordan canonical form? It's really, it's my favorite. It's kind of the coolest. It's kind of the easiest to wrap your head around. But does anybody know what the drawback to it is? It doesn't always work. If I just walk up to you on the street and give you a matrix, you may be able to turn it. You may be able to turn it into Jordan canonical form, or you may not. You have to be over an algebraically closed field. Or you guys remember eigenvalues and eigenvectors, right? To have a chance to do the Jordan form, all the eigenvalues have to be in the field. So if I gave you a matrix like this, is that right? Yeah. The eigenvalues of this are plus or minus I. And so this actually has a Jordan canonical form of the complex numbers, but if you're restricting yourself to real numbers, you can't do it. It's got a limitation. How many of you, this might be less prevalent, how many of you have ever seen rational canonical forms? Right. Where have you seen it before?
Homework in 8530.
Okay.
Very brief.
Gotcha. The rational canonical forms are a little bit more pain in the butt, right, in a certain sense. But the rational canonical forms may be suggested to their names always work, right? You can always do this. The Jordan canonical form is kind of a better, less sort of variant canonical form. But if you're not over an algebraically closed field, you run the risk that you might have a linear component that doesn't have a Jordan canonical form over that field. So, what's all this modules over PID got to do with linear transformation? Let me start with kind of a definition that you all are probably familiar with in the classes. Let A by the way, this notation I'm going to make, this is set in, or actually I should say ring, right? N by N matrices over F, where F is a field. Of course, you can generalize this to rings, but here I'm going to look at matrices of the field. Suppose that I have two matrices, square matrices, N by N over a field. We say that A and B are similar if anybody know?
Here's the invertible matrix. Much like a inversion.
So if you're an algebra fan, then what does this mean? Of course, you probably never hear this in an original linear algebra class, but really what that means is B and A are conjugates, right? That would certainly be true if both A and B were invertible, because then you're in a group of these matrices. But even more generally, even if these matrices are singular, then this is kind of a conjugacy thing that you would see in group theory, right? That's what a fancy algebra person might say. It's like, oh, that looks like a conjugate. Do you know what the significance was for similar matrices in linear algebra? So yeah, there's a definition, but who cares? What, does anybody remember what's important about two matrices, A and B being similar? They certainly, they share the same eigenvalues, right? But what it really means when A and B are similar is they are basically representing the same linear transformation with respect to different bases, right? That's kind of the big deal, right? So basically that means A and B are kind of, they're trying to represent the same linear transformation, only they're doing it with respect to different bases, right? And that's why you need P to be invertible. And so when you look at similar matrices, you're sort of looking at the same linear transformation with respect to different bases. By the way, how many matrices are similar to the zero matrix? Just zero. How many matrices are similar to the identity matrix? Well, what if A is the identity matrix? What happens?
It's only one.
It's only one. Right, because the identity transformation, it doesn't matter what basis you use, the matrix will always be the identity matrix, right? Whereas if you have a more exotic linear transformation with respect to different bases, the matrix may look different. So these equivalence classes aren't always the same, right? The identity only has one thing in its equivalence class, whereas a matrix at random may have a whole bunch, right? Okay. So of course, I'll leave this as an exercise that you all laugh at me about, but of course, similarity is an equivalence relation. So let me start off with the following theorem. Let's suppose that E is an n-dimensional vector space over the field K. Vector space. Over K. By the way, this is one of the cool things we picked up about free modules. E is isomorphic to E is very simple to me now, right? It's just n copies of K. And let phi from E to E be a linear transformation. So a K module homomorphism. So it's an old fashioned, good old linear transformation. And A, an n by n matrix over K. Now this theorem is going to kind of relate how these animals behave with respect to each other. There exists a unique monic polynomial . By the way, you all know what it means to be monic, right? It means, let me write polynomial first. This just means the coefficient of a leading term is 1. There exists a unique monic polynomial, I'll call it Q phi in Kx. Such that Q phi of phi is 0. And Q phi divides F for all F in Kx such that F of phi. So this first statement, number 1, is I can find some polynomial, some in fact unique monic polynomial, which I'll call Q phi, such that Q phi of phi is 0. So when I plug in this linear transformation, whatever that means, I get 0. And Q phi divides every polynomial with this problem. So if you find any polynomial in Kx that kills phi, then Q phi divides it. I'm going to make the same statement about the matrix. 2. There exists a unique monic polynomial we'll call QA in Kx such that QA of A is 0 and QA divides F for all F in Kx such that F of A is 0. And let me clear up, of course, when I say Q phi of phi, that 0 is of course the 0 linear transformation. And here F of A is 0, that means F of A is the 0 matrix. Finally, let me tie these together. 3. Yeah. A is the matrix for phi. Of course, probably back in the old days of linear algebra, you know, that if you have a linear transformation, you can write it in terms of matrix. And if A is the matrix for phi, with respect to some basis, for E, then polynomial is the same thing. Okay. Let me first let me first, before we go through this, let me make an observation here. Let me point out that that list of 3 things, these are all vector spaces over K. Right, like, especially the first one, right? Everybody's, that's one of the first things they're going to linear algebra when they want to give you vector space. What's the dimension of this? Is a K vector space. It is, it's infinity. In fact, I can explicitly give you a basis, 1 x squared is cubed, so forth, right? What's the dimension of that? It's just a K vector space. Which one? Correct. Right, because the matrix has n squared entries, and you can just take the sometimes you call the EIJ matrix the one that has all zeros except 1 in the IJ position. That's a basis for this. And so is this. Both of these are in dimension. I'm sorry, in square dimension. And the polynomial ring is infinite dimensional. That's gonna be a key observation here. So let's go through the proof of this. I want to prove really the first part because the others are almost exactly like this. Consider, okay, so I'm gonna give a homomorphism from KX to home KEE, given this linear transformation. Well, how could I do that? Let me think about what I want to do. My input is some polynomial. And perhaps depending on this linear transformation here, I need my input to be a polynomial and I want this to barf out like a homomorphism from A to E. Any ideas how to do it?
Express A's matrix.
Well, right, I'm gonna write this as a linear transformation. Like that. Let me point out what I mean by this. So for example, if F, so side there is A0 plus A1X plus ANXN, then by F of B, what I mean is A0 identity, right? Because I want to turn this into linear transformation, plus A1B plus AN B to be in Howard. Now notice B goes from E to E. So P squared goes from E to E as well. It's just composing it twice. And so each one of these are linear transformations from E to E. And when I multiply it by these scalars, that's another linear transformation. So when I plug in phi to this, I get this big fat new linear transformation, right? Everybody okay with that? So, from KX is a linear transformation. Right, because if you look, by definition, right. And now, before we break for the day, here's kind of a climax cliffhanger. You have a linear transformation here, I'm here to use it. Is it on to? Yes. I don't know, maybe. I mean, what if he was the zero polynomial, right? It might not be on there. Is it 1-to-1? That one is not even possible because the dimension of this is infinity. And the dimension of this is n squared. There is no way that this is 1-to-1. Agree? That means this has a non-trivial kernel. Right? And what's the structure of the ring KX? Anybody know? It's actually, well, that's a field. Does anybody know what's true of a polynomial ring over a field? What's it? It is. It's a principal ideal domain. So this kernel is basically going to be an ideal generated by a single polynomial. And that's where the Q phi is going to come from. And we will pick that up next time. Any questions on it? Any questions? All right. Well, y'all have a good one. Oh,